Hi. This video is now about the internal forces in the auxiliary air valve. I was particularly interested to figure out what kind of force this little finger exerts on the bimetallic strip, and would be interesting just to know what numbers we are dealing with, and this is what this is about. My particular interest was to figure out how the force changes with angle in this direction, and my reference angle was the fully closed angle, so I'm considering this here 0 degrees, and any number that I refer to, any angle, is starting at 0 degrees here, and then of course I count the angle from that position. So the two things that are important is that A, the spring extends and that increases the force. So I needed to measure the spring constant, and also the spring moves, as you can see, moves towards the center of rotation with increased angle, and that means that the moment around this point is being reduced, and that has an impact on the actual force that the spring exerts on the shutter here, and then on this little finger. So just as a short recap, once again, the way this auxiliary air valve works is by opening and closing an air gap that gives the engine additional idle air, and the bigger the gap, the bigger the airflow, and the idle RPM will increase. This is the center of rotation. Then we have a spring here that tries to pull the shutter closed, and down here we have a bimetallic strip that pushes in this direction. So these two work against each other, and as the engine heats up, or the bimetallic strip is being heated, it moves away in this direction, thereby closing the shutter and make it move counterclockwise. Okay, so the way to approach this is shown here. We have the length L0 when the shutter is fully closed, and then as this angle theta here increases, the point where the spring is attached to the shutter moves on a circular path, and so the spring will also change its angle compared to the to angle 0. We can approach this by using a square plus b square equals c square, except that of course here we have a square as the unextended length, or length at angle 0, L0, plus radius times the sine of theta here. That would be this line, and then this line is the radius minus the cosine of theta. So the whole radius minus this bit, and that leads to r square times 1 minus cosinus theta square plus length 0 plus r sine theta square equals L square. If we then use the trig identity cosinus square plus sine square equals 1, and after a bit of gymnastics this comes out. So the extended length is the square root of 2 times the radius times 1 minus cos theta plus L times L0, or L0 times L0 plus 2r sinus theta. I have calculated and measured this, and I'm in good agreement. I measure 25 millimeter and I calculate 25.19 millimeter for 46.8 degree, which is when the shutter is fully open. This leads to a periodic function for the force over the angle. That is a bit sharper at the lower end and a bit more rounded on the top end. But what we are interested is only roughly to let's say 50 degrees. That's the part that we are interested in. And here you see a comparison between the actual dysfunction in the interval over 0 to 50 degrees, and the orange line is if it were linear. So we are a bit off linear, but only 3% off linear at 48 degrees. Now what I also need to calculate is the moment arm. If I want to do the moment the spring puts on the shutter compared to the moment this little finger or the bimetallic strip puts on that little finger of the shutter. So the moment arm is 90 degree to the extended length and has angle alpha, which I see again here. So if I use that the tangent of this angle is r times 1 minus cos theta over L plus r times sine theta, and then I get this equation, and if I solve for the angle alpha, I have tangents to the -1 or arctang of this bit here. So the moment arm M is this length, and that is r times the cosine of angle theta minus alpha. So we have alpha here. We know it's r times cosine theta minus alpha. So it's r times cosine theta minus the bit that we calculated here. And once again, if I measure that, I measure 8.3 millimeter distance from the center of rotation to the spring, and I calculate 8.27 millimeters. So that once again is in good agreement. This gives an interesting function again. It's almost vertical in the upward branch and then pretty straight down to the higher angles. So if we plot this from angle 0, fully closed, to angle, I think here is 122, that's where it crosses over to 0, and that means nothing else than that the moment arm, or if it would work mechanically, this would be when the spring goes directly over the center of rotation. Then the moment is 0, and the moment arm is 0, and therefore the moment is 0. So I also need to measure the spring constants for the two springs, Bosch, which is stiffer, and missing parts, which is softer. And the results are shown here. The orange line is the Bosch spring, the blue line is the missing parts spring, and the force in a spring is a spring constant times the length plus another arbitrary constant c. That would be basically the unextended length of the spring. And what I measured with a piece of string and a plastic bag and M8 nuts in the bag pulling on the spring, I came up with these numbers. So the spring constant of the Bosch spring seems to be 267.3, and that would be Newton per millimeter, and this would be 184.15 Newton per millimeter. So basically then you multiply with your millimeter and the Newton stays and the millimeter get cancelled out, and that's the force that's actually exerted by the spring on the shutter. So in the end, I have my force in the spring is spring constant times the length of the spring plus the constant from the plot. And we had calculated the length earlier on as this. So if I substitute this for L this is the force that my spring exerts independence of the angle theta. What we also need to do is do a balance of moments. So basically the spring pulls the shutter counterclockwise with a certain distance from the angle of, from the center of rotation, and the bimetallic strip pushes this little finger in this direction clockwise and also with its own distance from the center of rotation. So the equation for that is that the moment, force times distance for the spring, plus force times distance of the bimetallic strip equals 0. In other words, the moment the spring exerts has to be cancelled out exactly by the moment the bimetallic strip exerts on the shutter, and it has to be 0, otherwise the shutter would move. So this is our basic equation, and if I solve that for bimetallic strip, I get F bimetal strip equals negative spring force into the spring times distance from the center over the distance of the center of from the center of rotation of the bimetallic strip. And this is the basic equation, and now we can put everything in that was calculated earlier on. So my moment arm M that we had calculated earlier was this, and M of course is what I called in the previous diagram D spring. So once again we have the equation F bimetal is F times F spring times distance from rotation spring over distance from rotation bimetal. And if I put my numbers in, the moment arm of the little finger is 9.14 millimeter away from the center of rotation, and the radius is 10.66 millimeter, and the unextended length, or the basic length at closed shutter, is 17.2 millimeter. And that gives this function, and I have turned it around, of course, since the force of the bimetallic strip goes in the opposite direction, it would be technically negative, but I went for absolute value here. So this is what this function does look like. It has this little hump here, and if we look at about one period, this is what it looks like. Here the red line is the missing parts spring, that is softer, and the blue line is the Bosch spring. So you can also see that this little hump is much more pronounced in that stiffer spring than in the soft spring, but this is of no concern. Once again, we go to about 50 degrees, so this would be the plot we are interested in. And you can see that we have a maximum force of on the bimetal strip of 3.93 Newton for the Bosch spring at 43.09 degrees, and 2.97 Newton for the missing part spring at 40.86 degrees. To put that in perspective, the force of 3.93 Newton corresponds to about 401 gram. That's the weight of 13.56 fluid ounces of water, and 2.97 corresponds to 303 gram, which would be 10.25 ounces of water. So it's quite a substantial force that's being exerted by the bimetallic strip on that little finger. Then I also did a comparison, just putting the original Bosch parts and the missing parts with the softer spring parts into the same auxiliary air valve to eliminate differences between them being a factor. And you can see here that the Bosch spring, this is both at 17 degrees Celsius. The Bosch spring has 26 degrees from that stop here, and you can see where on the red line that it sort of the whole counterpart of that adjustment screw on the back is exposed, or 3/4 of it, and the missing parts spring being softer rotates the shutter further open, and you go almost over the center of this. So that's the difference between the missing parts and the Bosch spring. That also means that you get more air at any given time, and this should make the car start easier and the warm-up should be better. So as conclusion, I can see that I have measured that the missing parts spring is about 2/3 of the stiffness of the Bosch spring, and with 267.3 Newton per meter opposed to 184.15 Newton per meter. The force characteristic is a bit convoluted, and that of course is that the spring, as it is being extended, exerts more and more force on the shutter, but at the same time it moves inward, and that torque is being reduced, which makes it a little bit easier on the bimetallic strip. So this is an overlaid effect, and that leads to the curve with the hump that I showed earlier. Interesting is that although the spring constants are a ratio of 2 to 3, the peak force ratio is about 3 to 4. And I have talked to the people at Missing Parts, and they said, yeah, they were shooting for a closing time of 4 minutes instead of 3. So this might be a coincidence, but I would say it's probably real that I measured the 3 to 4 ratio. And so also when the engine gets colder, the spring gets extended and the force on the bimetallic strip increases, and when the engine gets warmer, that force decreases. And since this air gap not being big enough, is the root of most starting and warm-up problems, I would expect that adjustment of the screw in the back here and using the softer spring should enable me to repair all the auxiliary air valves I have here and get good cold start and warm-up behavior. Thanks for watching.